Okay, yeah. So I think some people are excited about that, but it's also interesting because if you can efficiently make LIGO binaries and AGN disks and you can merge them, you might have an over density of LIGO sources in AGN disks or something.
Sorry, I have a question that might be dumb, but
yeah.
Are disks the only way that things accrete or end in planets form, or can you have more complicated geometries?
I think you can have more complicated things, but I think typically we think of planet formation as happening in disks, in my understanding.
Accretion.
Yes, I would say I'm not a planetary physicist as much, so I don't know all of the different ways, but
then like stellar systems where something's accreting.
Yeah, I think usually you have a disk of gas and it fragments at some point. You get two stars forming, and you might have more complicated accretion flows, but at some point you have two stars and kind of a circumbinary accretion disk that's feeding it the last layers of mass or something as it's building up. Yeah. Okay, so what exactly are we doing when we're doing this? So in our hydrocodes, we're solving the Navier-Stokes equations. So we're solving Navier-Stokes to get the disk dynamics, and then we're also looking at the orbital evolution of the binary, whatever flavor we're looking at. So here we're interested in the dynamics of the disk, the morphology of the disk, what's it doing, and also interesting because the disk can give us observational signatures for these different systems. And then for the orbital evolution, we're interested in the disk's impact on the binary. So we're curious for the binary, what's happening to the separation or the semi-major axis of the binary? Is it changing its eccentricity? How is the mass changing in the binary for each component? And potentially, how is the mass ratio of the binary changing in time? So like I said, each of these problems will have its own specifics in physics that you want to include. But the thing that I think about mostly is this problem of kind of compact supermassive black holes embedded in accretion disks. Let's see, maybe we'll go to here. So let's talk a little bit about supermassive black holes. Supermassive black hole binaries. Okay, and we'll think about this. A plot where we're going to look at the in-spiral time scale. So A over A dot in years as a function of the separation of the binary in parsec. So we'll have something here, so 1 parsec, and here we'll have 10 to the minus 2. Up here we can put like 100 parsec or something. Then here on the time scales, we'll have 10 to the 10. So this is going to be our Hubble time. Generally our Hubble time, and then we'll have whatever, something like 10 to the 8, 10 to the 6, 10 to the 4. Okay, so like I said, and this is kind of a classic picture from Regelman, Blanford, and Martin Rees in 1980. Okay, so I mentioned that we expect galaxies to merge. Our galaxies, many of them we expect to have supermassive black holes in their center. So to start with, we have some galaxy merger. So whatever, somewhere out here on like kiloparsec scales, you've got a galaxy merger. And so you bring two of these supermassive black holes together in kind of the resulting galaxies, it starts to relax. And these supermassive black holes start to move closer together by a process called dynamical friction. And we can think of this as like gravitational drag. So you've got these big black holes that come in, and you've got some stars, some gas, maybe some dark matter around. And these big black holes, they pull them in kind of closer to it gravitationally, but then they move forward in their orbit, and they have an overdense wake behind them that tends to pull on it, remove a little bit of angular momentum, and slow them down. So this causes the binary or the two supermassive black holes to shrink their orbit. And they do so they start shrinking their orbit by dynamical friction down to smaller scales. At some point here, they become bound. So the two supermassive black holes end up in a bound orbit. So here we've got our dynamical friction. But eventually, when we get down to our scale, like 10-ish parsec or something, this starts being, or our binary is getting really tight, and this stops being efficient. So then the binary has to shrink closer and closer together by something I'll call stellar hardening. So this is, you've got a more compact supermassive black hole binary. It doesn't have this drag anymore, but now it can shrink its orbit by individual interactions with stars in the field. So if a star has a sufficiently radial orbit or something that it can cross through the path of the binary, it can take a little bit of energy and angular momentum, slingshot away, and help shrink the binary closer together. Yes?
Say a bit more, what is the difference really between dynamical friction and stellar hardening? Is
I
it completely
guess
different things, or it's...
I don't think that they're super distinct. I kind of think of dynamical friction as kind of a large scale field effect where you're getting some wake of material behind it that's pulling on it, while the stellar hardening is like individual interactions with like a star that passes by the binary in less than an orbital time, takes a little energy and angular momentum, and then slingshots away.
So it's like, this is really, it's like three-body?
Yeah, it's like a three-body interaction.
Really
Yeah, well, this is kind of an interaction with the entire field of stars, gas, dark matter. But one of the issues with this is that as the binary gets tighter and more compact, it will eject all possible partners that it can interact with. And so it'll have no more stars with orbits that'll intersect it. And this timescale for merger can get really long. So this can come up here. And this is called depletion of the loss cone. The loss cone is just these orbits with the right phase space coordinates to interact with the binary. And when all partners get expelled by the binary, this loss cone gets depleted and the binary struggles to shrink its orbit.
But you surely replenish the lost cone, right?
Yes.
By stars interacting with each other.
Yes. So, as Andre mentioned, stars interact with each other. So you can replenish the loss cone by two-body relaxation. So stars interact with each other, and some of them get sent on to sufficiently radial orbits that they still interact with the binary. But the timescale for this can be very long, especially in your axis. Yes, in your axis symmetric scenario. So your timescale here is very long. We'll come back to it, but you'll notice, we're at times longer than a Hubble time. So if we want this to merge, we're potentially going to have some issues.
So this is what people call the last parsec problem.
Yeah.
Yeah, his plot is very careful. It is indeed a parsec.
Did I do it right? Yeah, okay, yeah, we're at a parsec. So you've got this two-body relaxation, and then eventually when you get down to about 10⁻²⁰ parsec, these massive binaries, you get this steep dependence, and this is our gravitational wave emission. So at around 10⁻² parsec, the binary starts emitting gravitational waves efficiently. It shrinks its orbit very quickly. We can eventually merge to 5. So we've got gravitational wave emission. And 6. They make gravitational waves, they shrink their orbit, they get down to zero separation, and they merge.
Can I ask a question as the voice of God?
Yes, voice of God.
If the dark matter was massive, imagine the dark matter was exceedingly massive, like tens or hundreds of solar masses for the particles for the dark matter. Would that change this story? Is this potentially a test of that?
Tens or hundreds of mass dark matter. Potentially, I guess at that point maybe you could have more complicated three-body interactions that could help move you more efficiently. I guess I'll talk about, well, let me talk about a little bit more of this final parsec problem and why it's not really a problem, and then maybe we can come back to your question. Is that okay?
Yeah, that's good with me. Thanks.
Okay, cool. So put this up for now, I guess. So what I mentioned there is that this, okay, so we jumped the gun. This is it, okay. So this stage 4, so if we want, or okay, let me see how to phrase this. Okay, so here we notice that this two-body relaxation time gets really long, or longer than a Hubble time. So theoretically, around this parsec, if you're just shrinking the binary with this two-body relaxation and this stellar hardening, you're not gonna be able to merge these binaries in less than the age of the universe. So you're gonna stall out. You're gonna have supermassive binaries potentially stuck at about 1 parsec separation. And this idea is canonically referred to, so I'll call it the canonical final parsec problem. And what this means is that if we want gravitational wave emission from supermassive black holes, so that we can measure it with things like LISA, or to see the gravitational wave background that we can measure with pulsar timing arrays, this would pose a problem because we're not getting them to a gravitational wave emitting phase. And then if we want them to merge, we have some good reason for thinking that we need supermassive black holes to merge, because we need to get really massive black holes at really high redshifts. This also would pose a problem. But that said, calling it the final parsec problem is a little misleading, because it kind of implies that we don't have solutions, which is not true. We do have solutions to this. It's only a problem in the sense that we don't really know which solution is the right answer. So our kind of the solutions that we can have for this final parsec problem, one is you can have efficient refilling of the loss cone. So if you don't take kind of your simplest picture of just an axisymmetric or whatever, symmetric distribution of stars, you start having some bars or some like triaxial things or some non-isotropic distributions, you can get more efficient redirecting of orbits, and you can shrink this time scale by refilling the loss cone by other means. Another one that maybe this gets to your question, will almost certainly happen at some point, is you'll have another galaxy merger. Like another galaxy will come and it'll merge and it'll bring its own supermassive black hole with it, and you'll get a triple interaction between supermassive black holes. So here, presumably we've got these 3 supermassive black holes. The least massive of them, generally speaking, will get shot out, and you'll shrink the orbit of the remaining 2. And maybe that's enough to get you into a gravitational wave emitting phase, or you stay stuck and this happens again and you have a triple interaction and you're shrinking the binary by triple interactions.
And the solutions would give different curves in your plot.
Yeah, so if you have you could have efficient refilling of the loss cone, and give you something like this. I'm not sure what your triple interaction would be, but it would depend on when galaxies come in. And then this last one, you can fix it with is gas. So if you have gas around this binary, it can remove angular momentum from the binary, shepherd it out to larger radii, and shrink it down. So your gas, maybe this kicks in, but then your gas takes over. It has some A dot that's less than a Hubble time that helps you merge. So all of these things can change this picture, and they give you a curve that stays below your kind of Hubble threshold and helps you merge binaries.
So is the probability of triple interaction is quite small? I really thought because you want another galaxy also to collide at the same time.
Well, it doesn't have to be at the same time. You have some galaxy merger, and say theoretically your binary gets stuck, and at some later time another galaxy is going to come. Yeah. Its black hole is going to undergo dynamical friction, and it's going to get close enough to these that it'll interact, and eventually it'll expel one of the binaries. It'll take away energy and angular momentum, and you'll get a more compact resulting supermassive binary.
Can I ask you something probably commitments, but how that time is measured by whom? Because maybe in Schwarzschild, some coordinate is very ugly defined, and time might say, okay, it takes a lot of time for something to happen, but it's just because we were parameterizing in this case the black hole. So this time that takes a lot to shrink the radius of the merger is which observer? Because I would feel that the proper time would be short for the guy when he's doing this.
Yeah,
Or
maybe.
not.
So I think this is from like our perspective, like as an Earth observer.
The whole distance is much longer than the horizon. So
Yeah. But at no point am I going to talk about distances that are so close to the horizon that we need to worry about relativistic effects and things.
So in this second scenario, don't we expect to see many galaxies with binary supermassive black holes there?
Or in general, I think we should expect to see many galaxies with massive binaries. I think an open problem is we don't see as many as we think we should. We have candidates for some of these dual AGN and big separations, but especially compact, like at 1 parsec or something, we see almost none of these. I think there's one candidate at like 7 parsec, and that's the tightest candidate binary we have right now.
And would you expect to see them?
So I think unless you can really efficiently move through here. So part of what I'm going to get to with talking about gas here is that we should care about this regardless of this problem about merging binaries. But if you can move really efficiently through here, then maybe you wouldn't expect to see them.
Right, but let's say there is a plateau, like the solid curve you drew. Would you expect to see the separations at 1 parsec, or no? Like how easy? Like could we not have observed them because they're just difficult to detect?
Yes, it's totally possible. If so, there are reasons to think that there should be gas there, and gas would give us a way to see these things. But if it's not there, they would be hard to see. The accretion rates could be really low, so they could be hard to see. So it's definitely possible that they could just be hard to find. And then even with our candidate observations, there are other ways like Doppler effects and things like that that you can use to explain these candidate observations. So they're also not even set in stone. But I think to answer your question, that yes, it could be hard to see. So it could be like an observational bias or something.
I mean, I think there's no evidence at this point that there is an excess of binaries at 1 parsec. I mean, a lot of us have been looking for it one way or another. So this, I think, is the strongest argument that there isn't fundamentally, the God doesn't have a 1 parsec problem, we do.
Yes, exactly. And that's the point I'm getting about. It's not that we don't know how to solve it, it's we just don't know what solution's right, and we don't know or what combination these come in.
No, but it sounds to me that like the second solution from that point of view doesn't look like a good solution, because the second solution I would expect that there should be lots of binary.
Well, there could still be lots of binaries. They could just be really hard to see as well. We'll have much better data when we do have if we do get a detection of gravitational wave background that tells us that we must have populations of compact binaries that are emitting gravitational waves. If we don't measure gravitational wave background, that would tell us something very interesting about this binary formation. And then Lisa can also tell us, we'll also be measuring mergers and be able to tell us about how frequently this occurs. But right now we're kind of dependent on electromagnetic observations, and those have not yielded kind of a large sample of observations of these supermassive binaries. Okay.
Can I ask yet one more stupid question, which is, you say gas, because gas can reaccrete into the system. In principle, dark matter can also reaccrete into the system. Is that definitely way lower order because of the lack of cooling, or is dark matter also potentially part of the quote gas unquote that you're talking about?
I'm not totally sure. So I don't know a whole lot about dark matter, so I don't know precisely. I think so I don't have a great answer to your question. I'm thinking mostly about canonical gas and not about dark matter and things. But you could probably cook up a picture where dark matter is important here.
Fine, that's fine.
No?
It wouldn't accrete, right? It's collisionless, like stars.
Oh,
They
sure.
would fly
Yes.
around and mostly do nothing, right?
Yes.
Yes, you only get the geometric accretion, I guess, of the dark matter, not even the bonding.
Yeah. Okay. So back to canonical gas. If no one else has questions. Okay, cool. So what I'm saying is that this gas is interesting. So I use this final parsec problem to motivate this. But this gas is interesting in its own right, even regardless of this problem. One, because generally we do actually expect it to be there. Because these mergers of galaxies and the tidal forces as these galaxies merge will actually drive the gas present in these galaxies down to small radii and down into the resulting galaxy's nucleus. And you can even have as much gas on the order of the mass of the binary that gets driven down to the center of the resulting galaxy. And then as we were just talking about, because this gas gives us observational prospects to potentially look for these things in the sky. So observational channels. So like I mentioned, we don't see a whole lot of these supermassive binary candidates, but we expect them to form fairly frequently from galaxy mergers. So there's work to be done to try to understand what are signatures of this that we could go looking for, and how can we conclusively say that there is or isn't a binary somewhere. Okay, cool. So there's some motivation. Now we can talk. Good time. Okay, so now we'll talk a little bit about what we're actually doing when we're studying and simulating these things. Talk about thin accretion disks. So in this picture that we're putting into our simulations, we're considering disks that are generally thin. And I say this because we're assuming that the gas is optically thick and radiatively efficient. And because of this, so the gas comes in, it has some angular momentum, and it starts to orbit around the binary. It's optically thick and radiatively efficient. It radiates away its vertical pressure support, and it collapses into a geometrically thin disk. So this disk is geometrically thin and rotationally supported. So and by thin, what we mean is you've got your object, your black hole here. You've got some disk, something like this, and there's the midplane here. This is the radius of the disk. At every radius, the disk has some scale height denoted h. And what we mean is that we take h to be much, much less than r. So h over r is generally regarded as very small. And if we consider our disk to be in vertical hydrostatic equilibrium, we can learn some interesting things about it. So our pressure gradient is balanced by our vertical component of the gravitational force. And if we impose this condition, this can be some characteristic pressure over scale height. Take this derivative, this GMZ for r cubed, and we know that our pressure goes like density sound CS to the sound speed squared. When you do this, you get that, solve for h over r, you get that this ratio h over r goes like the sound speed, g over r to the minus 1/2. But this is just our Keplerian orbital velocity. So this is, this goes like that, and this is the sound speed over our Keplerian orbital velocity. So this is the inverse of our Mach number. So this condition of vertical hydrostatic equilibrium in our disk, these really thin disks, tells us that the flow is highly supersonic, and that the sound speed is very small compared to the orbital velocity of the flow. So these disks are cold. So they're cold and supersonic. And then what do we mean by accretion?
Right, so I have semantical confusion. So if the disk is not thin, isn't it not a disk? Like the condition-
Yeah, exactly. So yeah, you can have. So we're talking about this limit where they're very thin. You can have whatever some people call them slim disks, where they're less thin. Maybe H is on the order of R or something.
But it's more really
And you
more
can
like
have
a
like
cone, right?
yeah thicker things that maybe technically you would call a torus or something like that. That gets more complicated. So I kind of call, if it's not spherical Bondi, I just say disk, but it's probably my bias because I'm thinking specifically about the situation.
Just
where-
like metals.
Yeah, sure.
Like carbon is a metal.
Okay.
In
Yeah,
astrophysical
yeah.
terminology.
Yes, exactly.
And what is the assumption about the profile? Like at H, does the disk just abruptly ends, or there is some like profile power law or exponential profile?
So it's some exponential profile at H. So H is really your the rate at which it's falling off exponentially in the vertical direction or something. This is kind of our contrived scenario. Much more realistic scenarios, you might not have constant H over R or something, or you have some corona up here or some other stuff. But we're doing simulations, so we like simple pictures that we can put in our computers. Okay, so and then by accretion, what do we mean? So by accretion, we mean that there's some flow of mass through a disk, m dot, which at each annulus r goes like the surface density of the disk times the radial velocity. Or here I've defined sigma, which is the surface it's the vertically integrated surface density of the disk. So now we're thinking about this disk in 2 dimensions, and this is like rho times the scale height h. And VR is negative, so that m dot is positive when it's flowing in, and then m dot would be negative if it were an accretion disk and flowing out. So dimensionally, this VR goes like the viscosity in our disk over the radius. So our disk has some viscosity that seeds some radial drift inwards. It's giving us some accretion rate m, which is allowing us to convert gravitational potential energy into radiation and creating things we can observe. So what is our viscosity here? Well, it can't be the molecular viscosity of the gas, because if you consider just the molecular viscosity, it ends up being very, very small. And the Reynolds number for our molecular viscosity is really, really big. Something like 10 to the 14 or bigger or something. So if we want to match observations from like AGN or X-ray binaries or something, just molecular viscosity between our ions or gas particles is not enough to get us sufficient accretion flows to match observations. So we need something bigger, but because this is so large, we expect our flow to be turbulent. So we can define some effective turbulent viscosity. So looks like some new turb, which will go like the characteristic size of the eddies in our turbulence times characteristic velocity of our turbulent eddies. Let's see, and this is a classic simplification from Shapur and Sanyaev, 1973. And what we say is well, the size of our turbulent eddies shouldn't be greater than the scale height of our disk, and the speed of our turbulent eddies shouldn't be greater than the sound speed in our disk. So we write our disk viscosity as alpha times h times our sound speed, where alpha is generally less than 1. So alpha here, so this is what we call an alpha disk. And alpha here is some kind of general parameterization of our ignorance. So we don't know exactly what is causing the redistribution of angular momentum, but we're saying there's some underlying turbulent flow that's giving us some Reynolds stress that's behaving on larger scales like a viscosity that we parameterize with alpha.
So what is M?
Sorry?
What is capital M?
Capital M. So this is mass. So this is m dot
Mass of what?
in the disk.
Oh, in the disk. But yeah, I'm just wondering, why don't we consider the dark matter? Because I mean, even though dark matter don't have any interaction with the baryon, but it still have a gravitational interaction.
Let's see, why not consider the dark matter?
Yeah.
Well, I guess with the dark matter, as Andre mentioned, it's just ballistic, flying around, might have some interaction, but
But you still have the gravitational interaction, right? Just I mean,
Mm.
consider all the dark matter distributed inside the accretion disk. You still have the attraction.
But the mass inside a radius will be fixed, right? Unless there's some like energy and angular momentum loss. So m dot would be basically close to zero.
Oh, okay, yes. But I mean, M will also still enter that.
Yeah, but the dark matter is there's also little dark matter. Gravitationally, it's subdominant in the core of galaxies compared to the supermassive black holes. Sorry.
So you said alpha is like the fudge factor.
yeah.
Like how much range is there? And can we cover it with simulations?
So people do try to do this, and so people do. So the general picture that people have is that you have some magnetorotational instability. So you've got some ionized plasma with magnetic fields. It's giving you some MRI turbulence. People try to measure what is alpha. You can get alphas that go from pretty small, but maybe something like 10 to the minus 2 to 10 to the minus 1 or something. But then there are kind of some more modern simulations that say, well, it's not right to even consider a constant alpha. Alpha has some radial dependence, or it can be locally dependent or something. So you can get very complicated even in just this general alpha prescription. But for kind of our simple problems and simulations that we run, we usually take alpha to be about 0.1. Okay, yeah, so just to wrap this up, we've got some disk, we've got our hole in the middle, and it's got some gas, and there's an m dot from our turbulent viscosity, and our angular momentum redistribution moves angular momentum to larger radii. Like I built out there, the parameters here that define the flow of our disk are the thickness of the disk and our output viscosity. And we generally take these to be constant in the disk, even though in a more complicated picture they could be variable in R or in R and phi or something. So now we want to take this disk and we want to put a binary in it. So that a binary. How does our picture change? So now we have our disk. Circles are hard. We're going to put our binary in. We have our binary black hole, or whatever binary, and it's orbiting. In the outer regions of the disk, you've got your inflow of mass, and angular momentum is being transported outwards. But as you get deeper in, this binary carves a cavity, but it's not a nice circular cavity. It turns out there's lots of kind of non-axisymmetric structure here. So the cavity that this binary carves is actually eccentric and lopsided. So it looks something like this. And the apsidal precession of this cavity goes around with some frequency that's on the order of 100 binary orbits. This binary this binary drives other non-axisymmetric features into this wall. So it drives, these spiral waves that can go out into the disk. And there's actually a density enhancement in this cavity that forms up here. So this is kind of usually referred to as the lump. So it's a density enhancement at the edge of the cavity that also goes around at something like once every 5 binary orbits. And then on orbital times, this binary is pulling streams off the cavity wall onto the binary. And these are filling up the individual Hill spheres of these binaries, so they get their own little individual disks, that we call mini disks. Let's see, so this one maybe has a stream there, and this one has a stream there. So you're getting all this structure in here, and you've kind of got three time scales going on. You've got the orbital time of the binary, where you're forming streams and filling these mini disks. You've got the orbital time of this lump thing, which is every 5 binary orbits. And then you've got the orbital time of the cavity itself, which is hundreds of binary orbits. Yeah.
There are some simple physical scaling to explain the like 500 why those values are what they are.
So the 100 something just comes from if you just calculate the precession rate of the cavity from the quadrupole of your potential. So that you can get intuitively. This 5 binary orbits, I don't think has an intuitive explanation. So it kind of pops out of simulations, and you can move it a little bit, varying your thermodynamics and things, but it's generally around 5 binary orbits for this lump period. And at least as far as I know, there's not a good theoretical explanation for why that is. I think we also don't fully understand why this lump even forms, like what's seeding this lump in the first place. And it's something that people are working on right now.
And in your simulations, do you start with a disk or you see how disk forms?
So we usually start with a disk, and then we run it for a number of viscous times, kind of in these inner annuli, to let it relax, reach some kind of quasi-steady configuration that looks like this, and then we study things about it. So the parameters we're left with in this problem, we have our disk parameters, so the thickness, the viscosity, and now that we've introduced a binary, we also have the binary separation, binary mass, binary eccentricity, and binary mass ratio. But 2 of these are arbitrary because they set the length scale and the time scale in our problem. So we don't have to worry about those. And these are the things that we have to set in our simulations. And then the kind of last thing that is left on the rung is the thermodynamics of the disk. In the simplest picture, you can just take the disk to be isothermal, or you could introduce some cooling or something, which can give you extra parameters.
Don't you also need the surface density of the disk
So,
as relates to the masses, right? Suppose my disk is infinitesimally
Yes.
light, then it will do nothing to my binary.
yes, so in what I'm going to talk about, we're assuming that the total disk mass is sufficiently smaller than the mass of the binary, so that there isn't a back reaction on the binary itself. So yeah, I'm going to be talking about the limit of disk mass is small.
So in
compared to
this
the binary.
limit, the orbit will not shrink.
Yes, sure, or at least on the will not shrink on sufficiently fast timescales or whatnot, but I think you can still get you get some quasi-steady configuration. You calculate the
And you-
shrinking. You
And
can get a time
perturbatively,
scale for
you can
merger.
perturbatively
Yeah.
calculate.
Okay, so we've got our problem set up. I wanted to keep this disk picture. That up. 15 minutes to talk about some results. Okay. Okay, so now let's talk about some stuff. We're putting this in our simulations, and among the many things you can look at in this problem, we've been looking recently at the orbital evolution of this binary. So like Andre mentioned, perturbatively, what happens to A dot, E dot, things like that, due to the presence of this disk. But historically, so for reference, historically people have done this. They've studied a kind of fiducial model for these disks all through kind of the 90s, early 2000s, and up until recently, where you consider an equal mass binary with it's circular. Like I mentioned, this alpha it's about 0.1, and then they consider H over R to also be about 0.1. And we generally think about isothermal disks so that we can think about these dynamics without having to worry about what the thermodynamics are doing. And what we want generally is to measure A dot and E dot in our circular equal mass case. If we, so how do,
black hole spin, does it play any role here? Or?
so in some of the most recent stuff, people have looked at how much are you spinning up the black holes, and they find that it's very small. So we're mostly just thinking about the orbital angular momentum. If you really want to keep proper bookkeeping of all the angular momentum in your problem, you do have to track the black hole spin, but we're considering just kind of non-spinning black holes. But again, we're still thinking about scales that are much larger than gravitational radii, so we're not worrying about GR effects or anything
Oh, but
that
it
could be introduced in the
affects,
spinning black hole.
because it affects how fast stuff falls into black hole, right? Because the last stable orbit.
Yes, yes.
I'm not sure, right? Because here you fix m dot, right?
Right.
So you are feeding the stupid thing,
Right.
and then it has no choice but to accept it, whether or not it is rotating or
But
not.
this m dot is what is fixed. By
M dot is fixed by some physics, right? Of how you feed the binary.
Yes, so m dot's either fixed by your prescribed surface density and viscosity, or you can say, oh, I want to prescribe some m dot.
Which
and
is
some
very
viscosity.
counterintuitive. I agree with
Yeah,
Sergey.
Because
Yeah.
maybe some
If you-
boundary condition is right?
Supposedly, the fate is decided at large distances. By the time it gets to the black hole, by the time it realizes the black hole is rotating, the fate of this gas is sealed. It has to go in. Some of it can be ejected by a jet, but this jet will have no back reaction to his.
Mm-hmm. And maybe we can come back to this. Like I'm not talking about the smallest radii and what we do for sync prescriptions and things like that. But if
But
you
it
want
is
to talk about it at the
counterintuitive, I
end, yeah,
agree
we
with
can
that.
come back to it. Okay, so how do we get these? Well, you can write. Let's see. Maybe what do I map for time? I have 10 minutes. So maybe I will just leave it at. Okay, so this is kind of the fiducial model that people have done before, and kind of in the early work on this, people found that when you do this and you study this problem, you get that the binary shrinks its orbit because you've got these kind of spiral features that lag behind the binary, that pull on it, remove angular momentum from the binary, and help it shrink together. But recently, in most of that work, when people were simulating it, they're actually excising the binary itself from the grid. So kind of the innermost regions, they aren't doing the hydro, they're just imposing this time variable kind of egg beater potential from the binary. So they're getting the disk, but not the innermost regions of the flow. More recently, people have done full global simulations of this problem, and they actually find that this A dot is positive for this fiducial model. And it's because when you include this innermost region, you actually get that these mini disks aren't perfectly symmetric. They're sloshing around, and they have spirals themselves and non-axis symmetries, and they give you positive torques that actually overwhelm negative torques from the outer disk and cause the binary to expand. So when you do the full problem, you get that the disk gives angular momentum to the binary and drives it apart, potentially inhibiting merger and maybe even reinforcing this final parsec problem that we talked about earlier. But one caveat to this picture, among many, is that I'm going to call this thinner disks. Is that this value of h over r of 0.1 that people were using previously, this comes from thinking about like protostellar disks and protoplanetary disks. But if we're thinking about our supermassive black holes, these compact supermassive black holes embedded in AGN-like accretion disks, we actually expect this to be much smaller. So this h over r for AGN is like 10 to the minus 2 or 10 to the minus 3. So the Mach numbers of our flow are 100 to 1,000. So one of the things that we did is we considered thinner and thinner disks. And one of the reasons this hadn't been done before was in part to compare with previous work, but also this is computationally challenging because these features in your disk go like h over r. So they define you need really good resolution to actually get converged results for these thinner disks. And it's only recently become possible.
How is it known like that they should be this thin? It's observation.
Yeah, from observations of AGN. So here if we look at A dot over M dot, and down here is the Mach number, so we're getting thinner as we go this way. We find something very simple that at Mach 10, this fiducial case, you get out-spiraling binaries, but as you go thinner and thinner, you get that this changes sign. And for us, this crossing point is at about Mach 25. So at least in this picture, if you're thinking about realistic thicknesses for disks, we find that if this trend were to continue, we only went up to like Mach 40 or 50 over here. But if you could go all the way to simulating these, we would expect them to recover this picture of gas shepherding them closer to merger and entering a gravitational wave emitting phase. But the reason for this is you can break this change in A dot into components from the physical accretion of mass and angular momentum, and that from gravitational torques. So the physical accretion of mass and angular momentum contributed very little to this, and it's fairly constant. But the contribution to A dot from our gravitational torques is what was dominating. So something changes about the morphology of the disk as you go to thinner and thinner disks. That's giving you a change in your orbital evolution.
Sorry, I missed. What's the horizontal line? What two things are crossing at the
Yeah,
crossing?
so I skipped over some of what I was talking about, but so the general trend in A dot is composed of, it essentially has three components. You can have gravitational torques that torque your binary, you accrete mass, which deepens your potential well and causes it to shrink its orbit, and you can accrete angular momentum directly. So this is the physical accretion of angular momentum and mass, and the one that is dominating our total sign, or our total change in A dot, is purely gravitational
Why
torques.
is it a dotted line rather than a solid line? Isn't it your axis, m-axis, this thing? Isn't it A dot becoming negative, or is it some?
So A dot is becoming negative. This is Mach
Why don't
number.
you put the axis
This
there?
is axis.
No, I mean this dotted line, isn't it zero?
This is 0.
Don't we have a convention when we start the axis from a zero?
Oh, maybe. Sorry, I'm not sure I follow.
That's why
That's what I'm
Josh
confused,
was
yeah.
confused.
Oh,
I
okay.
was-
It's a solid line with an arrow.
It should be a
to zero.
solid line, no?
Oh, okay. So this.
Yes, and put a M here or whatever.
Yes, okay. Sure. I'm sorry for the confusion. I'm trying to decide what to talk about. Okay. I guess we'll just finish talking about this. So what happens if you look at the radial distribution, just the average density profile of the gas. So here you've got your mini disks. So whatever this is at like 0.5. And then you've got your cavity depletion, and it rises up to the lump up here, and then it whatever falls away to your outer disk. So here, this is like 2.5 or something. And like I said, these mini disks here, these give you a gravitational torque that's positive, and your outer disk gives you a gravitational torque that's negative. And as we go to thinner and thinner disks, we expect some morphological change. What we see is that the mini disks stay about the same, so our torque there isn't changing. But then as we come up here to the cavity, we get a more and more dense kind of cavity wall or lump region here. So as we raise our Mach number, we get more and more mass here. And actually, if you look at the azimuthal distribution of gas in these systems, it's the same for all Mach numbers. So essentially, we're just piling more and more gas into the cavity wall. This cavity wall gives us characteristically negative torques because of its shape, and it's overtaking the sign of this binary evolution. The reason for this is you've got some, general inflow of mass from your circumbinary disk that's feeding in, but then because of this egg beater in the middle, you're getting these streams. But not all of that stream material goes into the mini disk. These streams are actually being flung back out into the cavity wall. So they're impacting the cavity wall, and they have some ram pressure. So this essentially buildup of material here has to be able to counteract the ram pressure from the stream so that the binary can, at least in an equilibrium situation, so that the binary can be pulling mass off and continuing to feed the streams. If you hit the cavity wall and you push it farther away, then you're going to stop making streams and you stop making impact, but m dot will bring you back closer in. So when you reach equilibrium, you hit this. But as you go to thinner and thinner disks and higher Mach numbers, you're getting colder and colder. So you essentially just need a higher density pileup in order to resist against the impact of the streams. Okay, cool. I got 2 minutes. Okay, maybe I should stop there. I was hoping to talk about eccentricity, but we can save that for another day.
That was like a minute fast.
Oh, is it? Okay. Okay, well,
Can you
how
fit
about
it in?
this? Yeah, I can put one interesting plot and talk about it. So this is some other work led by Jonathan Drake that we did. I forgot to put the papers in, but so if we plot here, so now we're gonna have, okay, I'll try to do this. So here, I'm gonna plot two things. These will be my zero lines. So here will be, so now we're considering this fiducial case, but with eccentricity. So we're looking at eccentric binaries. So you got E dot and A dot here. And what you find is that, and these are E. So as a function of eccentricity, your E dot looks like this. So essentially you find two equilibrium points, one here and one here. So this is telling us that things that start with very low eccentricity are driven to circular. You have this repulsor here at about an eccentricity of 0.1. So lower, you're driven down to circular, higher, you're driven up, and then your other equilibrium or attractor point here we found to be at about 0.45. And if you look at A dot for this, you get out spiral here, because again, we're back in this fiducial model, only changing eccentricity. But then it comes down, changes sign, and sits negative down here. So that if you have a circular binary, you might be expanding, but any binary that starts with some non-trivial eccentricity will be driven to this attractor eccentricity where it's shrinking its orbit. And then, I guess I won't get into detail, but this is astrophysically somewhat interesting because if you look at potential LISA sources, if they're driven to this equilibrium eccentricity by gas, and then they circularize through gravitational waves, they still retain enough eccentricity to be detected by LISA. So LISA could potentially tell us something about the importance of this gas-driven phase in supermassive black hole evolution. And then in a totally different scenario, if you look at distributions of, I guess I won't draw, but stars, certain types of stars that might have undergone some period of disk accretion, they actually have these kind of suggestive bimodal distributions that might be pointing at this kind of eccentricity evolution from the presence of a gas disk. Okay, I'll stop there.
Thanks, Chris. I have a question about the relationship between the gas solution and the potential merger solution. Is there any relationship between those? Like if a additional galaxy comes in and merges, would that disrupt the gas that is aiding you in merging the binary and have to start all over again? Or are those timescales so far apart that it doesn't matter?
Well, I think it depends on what your in-spiral time is from this gas. So I think I erased, oh no, so I put this, so if you, from this picture, if you work out where your in-spiral time is, if you're accreting at Eddington, you get that it's about this 10 to the 8 here. So that would help you through. I think then you wouldn't, but you could have another galaxy merger. I'm not sure off the top of my head what that second galaxy merger timescale is, but if you did throw a third supermassive black hole into this, that would definitely give you a more complicated picture of the flow. If it's coplanar, you'd have, you know, essentially two things in the disk going around, so two perturbers or something. but it could be out of plane and be punching through or something like that, giving you flares, and so it could definitely complicate your picture. Yeah, I think in general this picture can get very complicated, and at least we're trying to understand simple problems. And I think something I didn't properly mention is that even in this very simple case, there isn't much consensus on what actually happens. Only very recently did people start to agree on the sign of A dot in the simple case. It's in the last like 3 years have people agreed that, oh, in this case, you actually drive the binary apart.
But this thing accreting at Eddington, how long? Because we know that quasar stages are relatively short-lived. I mean, is it consistent with observations? Because if you want your accretion to drive the merger, you perhaps demand high luminosity of the...
Yeah, so I think in order to be less than Hubble, you only need to be like 1% Eddington.
No, but I'm asking like a very concrete question. We know total quasar light throughout the history of the universe. The existing quasar light plus your estimates of how fast this accretion occurs, do they allow your mechanism to be to merge all the supermassive black holes? Because I think you can do an actual estimate. I think we have a very good number, total quasar light. Like for example, Tremaine used total quasar light to put a limit of the spin of the black hole. Did you do this estimate? Given the total quasar light, is your mechanism potentially responsible for all the mergers?
We did not do it, but
because
we could talk
it sounds
about it,
like an interesting
let's do it.
estimate.
Yeah, cool. Anyone else have questions?
Any final questions?
Online? Oh, sorry, I missed the online question.
For project? Oh no, that's just discussion.
Oh,
I have. Can I hand a question? Is your that X? I mean, I realize it's slightly off topic, but that fundamental eccentricity of 0.45, is that really a kind of model independent kind of number, or do you think there's just some like different bimodal solutions in different accretion scenarios?
At least 0.45 definitely isn't totally model independent. There's another study that right after ours that did almost the exact same thing that found about 0.4. So you can definitely move it around. So I think we would more be saying, that depending on your specific problem, there's some bimodal solution for the eccentricity evolution.
Okay, good.
It's not exactly 0.45 in all cases.
That's very interesting because that's very observationally accessible in the giant planet world where we think a lot may form this way.
Yeah, and one of the things we're doing now is looking at eclipsing binaries that have really good eccentricity measurements, and we think we can show this bimodality.
Yeah, that's great. That's very promising.
Yeah. Okay. Anything else?
Any final questions? Second again.
Cool.
There should be coffee and cookies in the kitchen.
Normal stuff. Oh, we can show simulation type time. Nonetheless, it's okay.